Hello children, the continuation of semiconductors electronics, that intrinsic semiconductors. See, a semiconductor, we know that it is a material, the electrical conductivity which is falls between conductors and the insulators, right? Based on the level of impurities, we can classify the semiconductors into intrinsic semiconductor and extrinsic semiconductors. See, we'll see the intrinsic semiconductor in detail. uh, Intrinsic semiconductors, that is, we can say chemically that is pure. In other words, we can say free from impurities, that are termed as we can intrinsic semiconductors. See, the number of holes and the electrons are determined by their property of the material itself instead of the impurities. See, in intrinsic semiconductors, the number of excited electrons is equal to the number of holes, that is N, which is equal to P. See, you may see the valence bond model of the intrinsic semiconductor. With the help of that, see, the temperature of the semiconductor is increased. If suppose the electrons gain more thermal energy and thus break free from their cells. See, this process we can call it as ionization of the atom in the crystal lattice that creates the balance in the bond between the atoms. The position from which the electrons gets dislodged as a whole, which is equivalent to an effective positive charge. See, which you people are seeing on that is behind the valency in the covalent band. This valency of the electron, which is an effective positive electronic charge, that is what we said, it is a hole, right? As each free electron that creates one hole. So in an intrinsic semiconductor, the number of density of free electrons is equal to what we said, the number of density of the holes. So that only we are telling that Ne, which is equal to Nh, number of electrons, which is equal to number of holes in intrinsic semiconductors, right? And see the energy band diagram of intrinsic semiconductor. Suppose the temperature 0 Kelvin, the valence band of semiconductor is completely filled with electrons, while the conduction bond is empty. You may see on the diagram. And the intrinsic semiconductor, that time it behaves as an insulator at the temperature when 0 Kelvin. At higher temperature, for example, if suppose the temperature is more than 0 Kelvin, sometimes some of the electrons of the valence band gains sufficient thermal energy and it will jump to the conduction band, as you seeing on the next diagram, right? B, right? So this will show the B, which shows the T temperature which is more than 0 Kelvin, right? And at that time we can say that it gets it has some sufficient thermal energy to jump from that, right? The balancing bond to the conduction bond. So it creating an equal number of holes in the valence bond. So these thermally excited electrons occupy the lowest possible energy level in the conduction bond. So that only the energy band diagram of the intrinsic semiconductor at suppose temperature which is more than 0 Kelvin, right? And we can get clearly from the diagram the number of electrons in conduction band is equal to the number of holes in the balancing band, right? So see some limitations of the intrinsic semiconductors. In developing the semiconductor devices, intrinsic semiconductors have low intrinsic charge carrier concentration. That means of holes in the electrons. So they have very low electrical conductivity. And intrinsic charge carriers are always thermally generated. So that only flexibility is not available to control their numbers. And also for the intrinsic semiconductors, what we said, number of electrons which is equal to number of holes. So that they cannot have or a predominant hole or electron condition. This puts a limit to the usefulness of such materials. Yes, yeah. So for that, we have to know about the extrinsic semiconductor. So how the extrinsic semiconductors are producing, and these things we can see through the doping. So what is the process of doping? The process of deliberate addition of desirable impurity to the pure semiconductor, then only it will increase its conductivity. That we can call it as a doping. The impurity atoms are added, that we can call the dopant. The impurity atoms are called dopant. And the semiconductors doped with the impurities atoms is extrinsic semiconductor, or we can say doped semiconductors. Okay. So what are the essential requirement for that, right, for the doping process? See, the semiconductor material should be a very high purity. It should be it's maximum 100%. More than that it may be, right? 99.99% it should be a purest material. And the dopant atom should be neatly replaced, the semiconductor atom. And also the size of the dopant atom should be almost as the same as the semiconductor atom. The dopant atom should not know it's distort the crystalline lattice or structure. Like how? What are the methods of doping? See, by adding the impurity atoms to an extremely pure sample of a molten semiconductor, or else we can, by heating the crystalline semiconductor in an atmosphere containing dopant atoms or their molecules, so that the dopant atoms diffuse into the semiconductor, and we can by bombarding the semiconductor with ions of doping atoms, right? So what is extrinsic semiconductor? Before that, you must know what are all the types, the two types of dopants. By the methods, we will get the two different types of dopants, that is pentavalent dopant and trivalent dopant. Okay. Through the extrinsic semiconductor, we can know what are all the types. And extrinsic semiconductor means what we said, a semiconductor by doping, that means adding some impurities. So by doping a pure semiconductor with acceptors or donor impurity atoms, so it increases its conductivity, right? So it also has two types, that is N-type semiconductor and P-type semiconductor. See, the N-type semiconductor, we can say that there are the semiconductors obtained by doping with, for example, germanium or silicon with a pentavalent. P-type means the same germanium and silicon with trivalent dopant. So we can see the formation, how it is formed, the formation of the N-type semiconductor and the P-type semiconductor, right? See, the semiconductor is obtained by doping the trivalent semiconductor with a pentavalent impurities. See, for example, group 5 periodic table we can say, right? Arsenic, right? With the pentavalent impurity atom that substitutes the trivalent of silicon or germanium atom, it uses 4 of its 5 valence electrons in forming 4 covalent bonds with neighboring the Si atom, or we can say the silicon atoms, while the 5th electron is loosely bound to the impurity atom. So a very small amount of ionization energy, very small amount, maybe like 0.00 electron volt, it is required to detach this electron. And at room temperature, the thermal energy is enough to set free these electrons. The dopant atoms get converted into an ionized positive core now. So as each pentavalent impurity atom donates 1 extra electron for the conduction, that is only we are calling it as a donor. These semiconductors have free electrons contributed by the donors, and it is generated by the thermal process, while the holes are only due to the thermal generation. So that only we are telling the electrons are the majority charge carriers and the holes are the minority charge carriers here. As most of the current is carried by the negatively charged electrons, so the semiconductors doped with donor type impurities. That is only here we said that N type semiconductors. In that way, the N type semiconductors getting formed. So that is unbonded free electrons which is donated by the pentavalent. Got it? So how the formation of p-type we can see that p-type in the same way like it's doping with that the trivalent. Here we can take like tetravalent semiconductor same 4. Here also they are also tetravalent. We are here taking tetravalent with the trivalent. And what is happening? The impurity atom uses for the 3 valence electrons, forming the covalent bonds of 3 neighboring SI, right? So now the SI atom is left incomplete due to the deficiency of one electron, right? So an electron from the neighboring SI, if it's get, this hole is now available for the conduction. So the trivalent impurity atom becomes now a negatively charged when all its valencing bonds get filled. So now the trivalent impurity atom we can call it as a acceptor, because it creates a hole which can accept an electron from the neighboring bond. Obviously we can say there are holes created by the acceptor atom in addition to the thermally generated holes, while the free electrons are only due to the thermal generation. Here we can say the holes are the majority carriers, electrons are the minority charge carriers. Okay. So now the semiconductor which is doped with the acceptor type impurity, that's why we call it as p-type semiconductor. Got the differences between the formation, right? See the differences for your thing. N-type semiconductor, p-type semiconductor. What we said that N-type is obtained doping intrinsic semiconductor of pentavalent. P-type means we can take it from the trivalent. Okay, obtained intrinsic semiconductor with trivalent impurity. Electrons are the majority carriers here. P-type, their holes are majority carriers. Here N-type has donor energy level very close to conduction bond. Here in p-type acceptor energy level very close to the valencing bond. And in n-type temperature is, if suppose increased, means these semiconductors can easily donate the electron from donor energy level to the conduction bond. Here in p-type when the temperature is increased, here the semiconductors can easily accept an electron from the valencing bond to the donor energy level. Got it? Now the energy band diagram for the N-type and P-type semiconductors we can see of extrinsic semiconductors. See the N-type semiconductors, the extra electron what we said is very weakly attracted by the donor impurity. So a very small energy is required, we said, to free the electron from the donor impurity. So when it freed, this electron will occupy the lowest possible energy level in the conduction bond. That is, the energy of the donor electron is slightly less than the conduction energy. So the donor energy level, that is lies just below the bottom of the conduction bond, as you people are seeing on the screen. Like we can say for the p-type, here what we said, it's accepting. Each acceptor impurity creates a hole that can be easily filled by an electron of germanium or silicon covalent bond. So very small energy here also is very required to by an electron of the valence band to move into the hole, so that the acceptor energy level lies slightly above the top of the valencing bond. right?